Hello guys, Mr. G here with the second part of this test on Newton's law. This time we're going to be solving questions 3 and 4 and then we'll be done with this test. Okay? Question 3 said the block of mass 16 kg is rests on a rough horizontal surface. The coefficient of static and kinetic frictions are 0,3 and 0,25 respectively. A horizontal force of 45 Newton to the right is applied on the block as shown in the diagram below. You have this situation here. Question 3.1 state Newton's first law of motion in word, and they state that law real fast here. And this law state a body will remain in state of rest, or moving at constant velocity. That part is important. Either rest or moving at constant velocity. Those are very important parts in this definition. Unless a net force and not zero net force act on the object. That is Newton's first law that you have to learn. Draw the free body diagram for this object. We're going to do question 3.2 right here. Okay, now they're asking us to draw the free body diagram. So in this case, we are not going to include either components or we are going to include axes. So in this case, because it's 4 marks, we're only going to represent the force, but we're going to do real fast here, one with the axes just for control, just for us to know. This one is no for marks. The for mark one is there on the right side. So what forces are acting on this object? We have here the applied force. Okay, this is x-axis and this is y-axis. There is normal force, there is weight, and there is frictional force. There is frictional force. So those are the 4 forces acting. If you notice, the question is also 4 marks, so it's 1 mark per force. That is no 4 mark. This one we're going to do here is a free body diagram that they want, where there is not axis, there is not components, and this is all they want in this specific free body diagram. Okay, so this is frictional force, and this is question 3.1. Question 3.3, calculate the magnitude of the minimum force to put the body in motion. Now when they say minimum force, and this is important, minimum force to put the body in motion, they are referring to the maximum static frictional force. That is what they want. And let me show you something. In every test, if you go to the end of the test, you have the formulas. This is the formula for the maximum static frictional force, guys. That is what they want. Minimum force to put the object in motion. The formula is coefficient of static friction multiplied by the normal. So this is the formula, and the problem is, the only issue here is that you don't have the normal. You don't have the normal. Now, normal doesn't have a formula. You have to get the formula for normal. Okay, so this one is going to be 3.3.1. Okay, so we start by a static maximum frictional force, or maximum static is a static coefficient of friction multiplied by normal. And as we said, we don't have the normal, so we're going to get the normal now. Now, where do we get the normal? In the y-axis. Remember, we did it last time in the question. Here, guys, I show you, and I said you always have to do like that. Now, this one is simple, very simple, but I recommend you to follow the steps. To do this one, you say in y-axis, and then you apply it in y-axis. This one is very simple, but sometimes it's not going to be so. So here we have the net force is equal to 0, because in the y-axis the object is not moving. Normal minus weight is equal to 0. Normal is equal to weight, which normal is equal to mg, and that is what you must substitute there on top. If you substitute the numbers here, the mass is 16 and the acceleration due to gravity is 9,8. Alright, so when you calculate that one, will give you 156,8 Newton, and this value is the one we are going to substitute in there. So if you come here, maximum static frictional force is equal to the static coefficient of friction, which is 0,3 multiplied by 156,8, and this is going to be 47,04 Newton. This is the minimum force needed to put the object in motion, guys. I hope you understand that is an important term. And calculate the resultant force. Now, this one, even though it does not look too difficult, is a little bit tricky. Why? Because the minimum force needed to move the object or to start moving the object is 47,04 Newton. I want you to really look carefully here. 47,0204. But the force they are applying is 45. So 45 is not enough to move the object, and then the object does not move. The block do not move. Now, if the object do not move, I want you to know if the object do not move, and this I'm going to write it here. If so, then the frictional force, which is a static frictional force, the object is not going to be moving, is going to be equal to the applied force, which is in this case 45 Newton. I hope this one clear. Nothing to say. It's quite simple. The object is not moving. Why is not moving? The minimum force needed for the object to move is going to be 47,04, but the force applied is 45. It's not enough. So, saying that, how do you calculate the net force? So let's go here quickly. And this one is question 3.3.2. Net force is equal to applied force minus static frictional force. Okay, let's take off the symbol. Okay, now net force is equal to 45 minus 45, which is equal to 0. Now, if they don't ask you to calculate and they ask how much is the net force, and you understand what I said here, that the object is not moving, if the object is not moving, that one is Newton's first law, then the net force is equal to 0. But they don't say how much is the net force, they said calculated. So this one is the calculation. Is quite simple, but it's tricky. Okay, now the 45 Newton is removed with 80. Now 80 is definitely a different story. 80 is big enough, so the object will move. Calculate the magnitude of the acceleration of the block during the 4 seconds. Now this is going to be applied only for 4 seconds. Alright, so we are going to do it here on this little space. I think we have enough space, it's not that long. So here, this one is question 3.4. 3.4, F net is equal to MA, Newton's second law. Forces acting here, applied force, which is now 80, the frictional force, in this case is kinetic because the object will move, mass multiplied by the acceleration. The applied force is 80 now. I want you to note something. This frictional force is not the same as the one calculated before, because this one is kinetic. So this frictional force here will be equal to, this one here will be equal to kinetic coefficient of friction multiplied by normal. Kinetic coefficient of friction is 0,25, and the normal was already calculated, so I'm not going to recalculate it. It's 156,8. Normal stays the same because nothing else changed but the applied force. So the kinetic frictional force is going to be equal to 39,2. And you can notice something important: the kinetic frictional force is always smaller than the maximum static frictional force. That is an important detail here. So if you substitute everything, you'll have and because they're asking you for the magnitude of the acceleration, you don't have to give direction. So this question is almost done. Now they say if the same force of magnitude 8 Newton is applied on the block forming an angle of 30 degrees with the horizontal, will the acceleration be now greater than, smaller than, or equal to the acceleration calculated in question 3.4? Give a reason for your answer. Alright, I want you to understand this one real fast. For this question they say that now the applied force is going to be having an angle of 30 degrees with the horizontal. This is the new free body diagram now. So here in the x-axis you won't have Fa, you will have Fa in x, okay? And this one will go to the y. It's not part of the problem, but Fa in x it is. The acceleration, remember, F net is equal to ma, okay? So here we have now Fa in x minus friction equal to ma. So A will be equal to Fa in x minus frictional force divided by mass. Okay, now what is the issue here? Previously was equal to, this is before, let's not do that. Before was just Fa, it was the force applied in x. Now Fa in x is going to be smaller than Fa. In other words, Fa in x will be less than 18 Newton, and therefore the acceleration will be smaller than. So the question here is smaller than. That is the answer. Explanation why? Because F applied in x is smaller than the F applied and is smaller than 18, not smaller everything, and Fa in x will be therefore smaller than 80 Newton. So the acceleration is smaller. I hope you understand that one, and that will be the end of question 3. So that is question 3. It's a good question, it's not too bad, it's a little bit tricky here and there. It's easy but tricky. Let's go to question 4, which is a little bit even more tricky. Now this is a good question, I like it, it's interesting. They say two steel crates of mass 50 and 30 kilograms are in contact and at rest on a horizontal surface. A 600 Newton force is exerted on the 50 kilograms crate. Okay, crate as the system moves with constant acceleration. The coefficient of kinetic friction between the surface is 0.15. State Newton's third law in words. Okay, and here is Newton's third law of motion. When object A exerts a force on object B simultaneously at the same time exert the force on object A equal in magnitude and opposite in direction. In other words, the force that A exerts on B will be equal to the force of B on A, but opposite in direction, that is the minus at the front there. This one is Newton's third law, guys. This one is Newton's third law. It is important. It's going to be asked. We may be asked in the exam. It's an important law. Okay? Now, second, 4.2. Draw the level free body diagram showing all the forces acting on the 30 kilogram crate. But now, here is a little bit tricky, the question. I want you to know that this crate here, this one, is exerting a force on this other one. Okay, so this force will be pointing there. That one is the force from the 50 kg on 30 kg, and here on this block will be the other force in that direction, which is the force of 30 kg on 50 kg. Those are the two forces on each other. That is Newton's third law, guys. That is the Newton's third law here. This is the action-reaction pair. They are acting on different objects, okay? Now let's draw the free body diagram for each object here, okay? So let's do that question real fast. This is 4.2. But let's do for both. They're asking to do it for only one. They're asking us to do it for the 30 kilogram, but we are going to do it for both because we need it later on. We're going to do first the one of 30 and we're going to do the other one. They don't want the axis. Remember, I told you they only want the forces. So now if we go here to this specific object on the 30 kilogram blocks, what forces are acting there? As we represent here on that object, this is the first force that you can see there, the force from the 50 on the 30. Okay, what other forces are acting there? Well, there's also friction. There's also friction in the opposite direction on this object. This is friction. There is normal force and there is weight. So those are the forces acting on that specific object of 30 kilogram block. And that is the free body diagram we are going to draw here. Here we have the first force, which is the force from 50 kg on 30. I'm going to write it like that. If the object were given names A and B would be easier, but it does not really matter. What else? We have the normal force straight perpendicular to the surface. We have the weight, let's write weight, gravitational force, if you may, and then we have frictional force. There we go. That is for, let's write the T on top. This is for 30 kilograms. Now, for 50 kilograms, this is not part of the question, but we're going to quickly do it. What forces are acting? If we go into the 50 kilograms now, the one on the left, you can see the force from 30 on 50, but this one is also an applied force to the right, plus the normal friction and weight. So there is going to be an applied force to the right here, that is the applied force, which is 600 Newton, I think. It's 600 Newton, this is the applied force. Yes, it is. Now there is the normal, let's write the normal first. We have the weight here down. And now on the left, we have two forces. We have, first of all, the friction. And we have also the force. This one is the force from the 30 kg on 50 kg, which are the same. That is Newton's third law. And that is the free body diagram for the other object. They only ask for this one here, guys. They only ask for this one here, but we did both because we may have to use them. Okay, so let's go to the next one, which is now the most tricky in this question. Let's say calculate the magnitude of the acceleration of the system of the two steel blocks. Now, here, this question is not that bad, but they don't like to use the work of the as a system. We have to work simultaneously with two different equations, and we are going to really quickly do that. This is question 4.3.1. The first thing we need is the two free body diagrams. That's what I did it. And then I transfer here the two free body diagrams. So here on the left, we're going to write for the 30 kilogram block, and on the right for the 50 kilogram block. Which one you work first, it doesn't really matter. So in this case, let's start with the 30 kilogram block. Remember, we're looking for acceleration. So we're going to apply Newton's second law. F net is equal to ma. Okay, what force? We're working in x. I recommend you to do this one, but if you don't want to do it, it's also fine, guys. It's not a big issue. It's not the must, okay? This is the x. I recommend to follow the steps, work on the axis, and so on. So here we have this one. What forces do we have in x? We have the force of 50 kg on 30 kg minus frictional force equal to ma. This is what we have on this side here. Now, if we notice here, we don't have the force from the 50 kilogram block on the 30, we don't have friction, and we don't have acceleration. However, friction can be calculated. And we did calculate it before. Friction can be calculated, and we did calculate it before, so I don't want to spend too long time calculating something we calculate before here in a previous question, guys. I'm going to show you quickly. You can go back and watch how to calculate how to calculate the normal on this point here, because you need the normal, and here how to calculate the kinetic coefficient of friction. So I am not going to repeat it Now you can go back there in the video and watch it. So here, now when you do that one, you will get this one is equal to so if we substitute here what we have, now we have two unknown, but we cannot calculate none of them. So we are going to stop here and we are going to call this we have equation 1. This is going to be equation 1. Okay, so now here we are going to do exactly the same. We are going to apply Newton's law for this object here, guys. It's the same application of Newton's law for this object in x-axis. Let's write here in x-axis. I like to work like that. You don't have to do so. So in the x here we have a little bit more force. We have the applied force minus friction minus force 30 on 50 kilograms equal to MA. And now the frictional force, again we don't have it, but it can be calculated in the same way as before, but it's the different mass. Everything else is the same. Once more, we have two unknown, so we are going to stop here and we are going to call this equation equation 2. This is equation 2. Now, this is important. This is the Newton's third law. This is the same as this. So we are going to equate and work simultaneously with these two equations. I personally like to add the two equations, but you may use substitution if you will. So I'm going to add the two equations. And here is the answer for the acceleration of this object. Okay, calculate the magnitude of the acceleration, so no direction needed. I hope you understand this one. It's a very good question for test, guys. It's a very, very good question. So now calculate the magnitude of the force that the 50 kilogram steel crate exerts on the 30 kilogram steel crate. So all we have to do is use either equation 1 or 2 and substitute the acceleration, guys. It's quite simple. So we can use any of them, and this one will be question 4.3.2. so we're going to use either equation. In this case, let's use either equation because it's the same, but in this case we're going to use the first one because it's the one they ask you for the force of 50 on 30, which is the equation 1. So we are going to write that equation here and we substitute. The answer is 225 Newton, and that is the end of this other question. Now, if we go to the final part of the question to really finish this question 4, question is a little bit long. How would the magnitude of the force that the 30 kilogram steel crate exerts on the 50 kilogram steel crate compare to your answer in question 4.3.2, guys? Is equal to. Here is the answer, equal to. Why that so? Newton's third law. Explain your answer using a relevant law of physics, and the relevant law of physics is right here. The force that the crate of 50 kilogram blocks exert on the 30 is the same as the other one, but in the opposite direction. So I'm not going to write that one because the answer is right there. It is Newton's third law. But guys, this is the end of this video. Thank you for watching. I hope it helped. The video was extended more than I thought it was going to be. I don't like long videos. I know you get boring. This is physics. If it was Netflix or a movie, you will enjoy it. But thank you for watching. I hope it helped, which is the main purpose of these videos. Thumb up, subscribe for the channel. I'll see you next time. Mr. G here.